In this video, we will discuss what is called the fundamental counting principle, and it allows us to count the number of ways we could perform a certain task if we can break it up into multiple independent steps. So we'll begin with the definition, and then we'll start applying this to various examples. So the definition begins by saying, consider a task that could be broken down into k consecutive steps. So here k is just representing any number that applies to that particular problem. And by consecutive steps, we means we could do the first thing, then the second thing, the third thing, so on and so forth. So in our example, we have step 1, step 2, all the way up to step k. And suppose for those individual k steps, we know that in order to accomplish step 1, that could be done in subscript 1 ways. So you knew exactly how many ways step 1 could occur. Similarly, you knew exactly how many ways step 2 could occur. We're calling that in sub 2 just for labeling purposes. So our subscript aligns with the step that we're on. All the way up to step k occurring in sub k ways. Here. Then the fundamental counting principle says if you know how each step would occur in so many ways, then the number of ways the entire process occurs is by multiplying together the amount of way each of the individual steps would occur. So the overall k-part task would occur in sub 1 times in sub 2 all the way up times in sub k. So the way I like to think about this particular rule is the number of ways an entire multi-step process could be accomplished is the number of ways each individual step occurs all multiplied together. So in our first example of this, we're asked how many ways is there to create a 2-digit number, and this 2-digit number that we're trying to create will be based on the digits 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then they give us this important clarification. Assume that we can repeat integers. So for instance, I could have the digit 1, 1. And for this particular chapter, we're going to use this phrase with repetition or without repetition so often that we will usually, instead of saying assume allow repeated integers, we'll just shorten that to with repetition. So look for that in future problems. So potentially I could begin this process by listing out all of the 2-digit numbers that are made up of the digits 1, 2, 3, 4, 5, 6, 7, 8, and 9, allowing repetition. But that would be a tedious process, and I'd have to be sure that I did it very carefully to make sure I didn't miss any digits. A more efficient way would be to realize that in order to count the number of 2-digit numbers, that's a 2-step process. The 2-step process is found by picking the first digit, so I'm just going to kind of make a little box here to help us visually focus. Pick the first digit. And after we pick the first digit, to finish up the process, we have to pick the second digit. So as we're working on this problem, do stay focused on the fact that this is just helping us organize our thoughts. There's nothing mathematical to these boxes or brackets. We just learned that the number of ways to do a multi-step task is the number of ways the individual steps occur multiplied together. So if I can figure out how many ways I could pick my first digit, and then I could figure out how many ways I could pick my second digit, then this rule tells me if I multiply those two things together, I will have solved the overall problem. So let's think about how many ways could I pick my first digit. It goes back to what digits am I allowed? I'm allowed to use 1, 2, 3, 4, 5, 6, 7, 8, or 9. That is 9 different options. So when I write this 9 here, I'm not saying I'm picking the digit 9. I'm saying there are 9 possibilities. The 9 possibilities are choosing either 1, 2, 3, 4, 5, 6, 7, 8, or 9. Now when it comes to picking my second digit, my reasoning here not only is based on what digits they allowed me to use, but if I'm allowed to repeat integers. So for instance, once I've picked the first digit, that choice is done. I've picked some number. And since it says I can allow repetition, that means I technically could choose the same digit again for the second place. So I don't have to eliminate any choices because it's okay if I repeat. So since I'm allowed to repeat, I still have 1, 2, 3, 4, 5, 6, 7, 8, 9 options. So I'm going to write another 9. Again, I'm not saying I'm picking 9. I'm saying there's 9 options here. And then to use this rule, it says if you multiply the number of ways each step could occur, that resulting value, which 9 times 9 is 81, means there's 81 ways to pick or to express with repetition. In our next example, we're asked how many ways is there to create, again, a 2-digit number. And here we're asked to use the digits 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then they add the caveat that we do not allow repeated integers, said more efficiently in future problems, without repetition. So since it said a 2-digit number, we can say this overall process, we want to think, how could I break it down into more workable, smaller chunks? So instead of picking the 2-digit number and figuring out how many ways that could occur, let's say, how many ways could I pick the first digit? And I use this brace as just a helpful visual reminder. And then after you pick the first digit in a 2-digit number, you have to then pick the second digit. So next comes picking the second digit number. And I know I need to figure out the number of ways that could occur. Okay. So for the first digit, you say I was allowed to use 1, 2, 3, 4, 5, 6, 7, 8, or 9. That's 9 different options. So I'm going to write down there's 9 ways I could pick the first digit. Again, keep in mind this is not saying I'm picking 9, I'm saying there's 9 ways. But once I've picked that first digit, let's say for instance as an example to think about this off to the side, let's say I picked 3 first. Based on what's highlighted in purple here, would I be allowed to choose 3 again for the second digit? Think about whether you'd answer yes or no there. If I've already picked 3 as the first digit, would I be allowed to pick 3 again as the second digit? No, that's not allowed because they said we could not repeat integers. So whatever we've picked for the first digit, it cannot occur again in the second digit because they said no repetition. Now, how do we take that idea and apply it to counting? Well, we don't actually know what digit I picked first. The whole part of this process is it's leaving it somewhat abstract. We're just counting the options. But whatever one of these digits that we picked first, there was 9 originally available to us. We've already used one of them here. So what we've done is we've said one of the things we can't use again. One of the 9 things cannot be used again because that would create repetition. So how many remaining options are there available to us? Only 8. Because we have to exclude the item that we used at the beginning, whichever one of those digits it occurred to be. And then finishing up this problem, once we've been able to break down the process into consecutive steps and figure out the number of ways each of those steps could occur, the number of ways the entire process occurs can be found by multiplying the number of ways the steps could occur separately together. And that would give us 72 ways to create a 2-digit number using the digits 1, 2, 3, 4, 5, 6, 7, 8, 9 without repetition. Contrast this with our previous example. You notice the previous example had the exact same setup, except for their difference here. The first example allowed repetition, and the second example said no repetition. The way those differences are expressed in the way we solve the problem is when we're allowed repetition, I still have all the original options available in the second step because I'm allowed to repeat. Whereas whenever we can't have repetition, I had to decrease the number of options available to me in the second step because I couldn't use whatever digit was chosen for the first digit. Originally, there were 9 options available in the first digit, but once you've picked your first digit, you now have 1 less, or 8 options available for the second digit. Next, we are asked to consider a club made of the individuals whose names are labeled A, B, C, D, E, shorthand for Alan, Bill, Kathy, David, and Evelyn. We are asked to consider in how many ways could this club elect a president and a secretary under the restrictions that no one may hold more than one office. This is a lengthy way in context of the problem to say without repetition. And additionally, we have the additional restriction that the secretary must be one of the males in the club. Now, for this particular problem, before we get started solving it, I'd like to highlight this useful problem-solving strategy to keep in mind in your future homework problems. Whenever one or more parts of the task has a special restriction, you should consider dealing with that special restriction before any of the other parts of the task. The more restrictions that are involved in one piece means you should deal with that first, and it's going to make the whole problem-solving process much easier. So it does matter what you focus on first. Now, with that in mind, what do you think is the extra restriction we have in this problem? Take a moment to read through it again if needed. The special restriction in this problem is that the secretary position cannot go to anybody in the club. There is a restriction based on how this problem's phrased that the secretary position must go to a man. Now, we were going to pick 2 positions. We're going to pick the president and we're going to pick the secretary. Take a moment to reread this example and ask yourself, are there any restrictions placed on the president? As we read through this example, we see there's no restrictions specifically placed on the president. However, anybody that I choose for the president cannot then be chosen as secretary because it says nobody can hold the same more than one office. So whoever we choose for one office can't be considered for the other office. Now, I know this is somewhat new to us, so it's going to take a bit of time to get in this frame of thought, but I'd encourage you to focus on it through this rest of this video. All of these problems involve seeing that this whole process, instead of thinking of it all together, which is complicated, I could break it down into pieces or consecutive decisions. Once I've broken it down into consecutive decisions, I can focus only on how many ways could I make this decision? Okay, then how many ways do I make the next decision? Once I know the number of ways I make each decision, our rule tells us that you can just multiply the number of ways each decision occurs, and that will give you the number of ways the whole task occurs. So for this particular problem, take a moment and think, how many decisions do I have to make to complete the problem? What would you describe them as? The first decision is picking what? The next decision is picking what? So since we're choosing somebody to be the president and somebody to be the secretary, I would say in general there's 2 different steps. Picking the president, picking the secretary. And I can do those in either order. I could pick the secretary first and then the president, or I could pick the president first and then the secretary. Now, in particular, we've learned the idea that if some position has extra restrictions, we should deal with that first. So what that means for us is we should pick the secretary's position first because it has the additional restrictions. So in order to help me visually kind of focus on what's going on, I like to draw these little brackets, and that helps me focus. This is this decision, and I always label what I'm looking at. So this is how many ways we can pick the secretary. Now, the only rule that we have to follow in picking the secretary is the secretary must be a man. Now, looking back at our club, Alan, Bill, Kathy, David, Evelyn, I see there's 3 candidates. Alan could be picked, Bill could be picked, David could be picked. So how many ways can we pick the secretary? Well, there's 3 people available who fit our criteria. So 3. Now we've picked the secretary. The next decision that comes to play is how many ways can we pick the president? Now, once we've chosen our secretary, we know it's one of the 3 men in the club, so it's either Alan, Bill, or David has been chosen as the secretary. How many people are now available to be chosen for president, keeping in mind that nobody can hold more than one office? As you think about this, take a minute or 2 to reread the problem, rephrase the question, pause the video and attempt it on your own, and then unpause to check your work. Again, your question is, you've already picked the secretary. It is one of the 3 men who are originally in the club. You know that one person cannot hold more than one office, so how many individuals remain to be picked for the position of president? So the idea is we had 3 men originally considered for the position of secretary. One of those men was picked for that position. So now, since nobody can hold 2 offices, that person who is picked for the secretary position cannot be considered again for the president's position. So now we have 2 men who could be considered for president. We don't know which 2, but all we have to know is the number of them, not particularly who it is. 2 men considered for president. Plus, now, since there's no gender restriction on the president's position, based on how this problem's worded, we can go back and say Kathy and Evelyn could also now be considered for president. So that adds 2 women. So altogether, there are 2 men in the running for president, along with 2 women in the running for president. That makes a total of 4 people in the running for president. Now, this process, they said pick a president, pick a secretary. We have outlined how many ways you could pick a secretary based on the restrictions of the problem. We've outlined how many ways we could pick a president based on the restrictions of the problem. And we know if you can figure out how many ways each individual step occurs, then you can figure out the total number of ways this could occur by multiplying the individual steps number of ways together, and that will give you the overall total number of ways this could occur. So there are 12 ways based on this club membership and these restrictions that we could pick a president and a secretary. Some states have license plates which have 3 letters followed by 3 digits. How many such license plates are possible? They then tell us the important piece of information that we are to assume that you can repeat digits or letters. Now, in these problems, in order to be successful, we need to say, okay, they're asking me how to do an entire process. We're not good at determining how many ways an entire process could occur. However, we are able to determine how many ways individual steps could occur. And then by the fundamental counting principle, we know that it's mathematically true that if you know the number of ways each step could occur, multiply all of those individual number of ways together, and you get the number of ways the entire process occurs. So looking at this process, picking license plates, as described, that have 3 letters followed by 3 digits, how many steps do you think or decisions are involved? Well, first up, we have to pick the letters. So we have to pick the first letter, then we have to pick the second letter, then we have to pick the third letter, followed next by the digits, and they said there's 3 digits, so we have to pick the first digit, the second digit, and the third digit. So picking the letters and the digits means 3 choices for the letters in a row, 3 choices for the digits in a row. So that's 6 different steps in the process. Picking the first letter, picking the second letter, picking the third letter, then pick the first digit, the second digit, followed by the third digit. So the entire process is broken down into these 6 separate steps. Now we just have to figure out the number of ways each of these steps occur as an individual, multiply them all together, and that will be the number of ways the entire process could occur. Now when they say we could pick from 3 letters, we take that to be the letters available in the English language. And there are 26 letters in the English language. So as we pick our first letter, I could pick from any of the 26 letters of the English language. Now in terms of picking the next letter, we need to ask ourselves, can I repeat digits? For instance, could I have the sequence AAA? It said repetition is allowed, so I could pick from the same 26 letters again because it's okay if I end up repeating the same letters. So there's 26 ways to pick the second letter. Okay, think to yourself, how many ways are there to pick the third letter since repetition is allowed? That would be 26. Now we need to pick the first digit. Now, in some problems, they tell you particularly what digits are you allowed to choose from. And if that's the case, definitely look at those and then count how many options are there available. But in this particular problem, they just said 3 digits. So unless specifically specified otherwise, if they just tell you pick from the digits, you're to assume that you could pick from the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that is in total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 options. So there's 10 possible digits that we could choose from. So the number of ways to pick the first digit is 10, and since I'm allowed to repeat, I could pick all 10 digits I can choose from for the second digit, along with the next one. Now, in order to figure out the number of ways the entire process could occur, because right now we've just done step by step, you multiply all these together. Now, this is going to be an extremely large number. Some of y'all's calculators won't even be able to calculate it. It will give you something in what we call scientific notation. So when the number of ways something could occur is very large, what we can do is instead of writing it out in scientific notation or a very large number with many, many digits, we can use exponents to say 26 multiplied by itself 3 times is written mathematically 26 cubed. Times 10 multiplied by itself 3 times is 10 cubed. Because repeated multiplication can be expressed as exponents. 10 times itself 3 times. 26 times itself 3 times. And that's how we go about this problem. For additional practice, let me now change the problem slightly, and let's see how that would change the way the problem's solved and how many options would be available to us. The change that I want to introduce, and if you want, write this on a separate piece of paper, it's a new problem, is now repetition is not allowed. And that's the only change I'm going to make. It's still going to make a license plate made up of 3 letters followed by 3 numbers. But now we can't repeat, so I can no longer have the license plates that are like AAA 111. I could have the license plates that are like ABC 123. So any digit or letter that appears once can never occur in subsequent locations of the license plate. So keep in mind this is a completely new problem, and we're determining how many ways we could do the license plates with 3 letters and 3 numbers if we do not repeat any letters or digits. So take a moment to think to yourself, how many ways could we pick the first letter? if we're picking from the 26 letters of the English alphabet. There's 26 ways. Any of the 26 numbers we could pick first. Now keep in mind, in this problem that we're thinking about, of the 26 letters available, we have now used one of the 26 letters as our first digit. And since I cannot repeat digits, I no longer can use that digit again in subsequent choices. So since I've used up one of them, 26 minus the one I've used means there's only 25 letters available to choose as the second digit to avoid repetition. Okay, follow a similar train of thought and think, how many ways could you pick the third letter if we're avoiding repetition? Okay, originally there was 26 letters available. However, I've already used up one and then two of the 26 letters available. I can't use either of those two again, so 26 minus 2 leaves me with 24 options left. Okay, I'd encourage you to pause the video now and, thinking in similar patterns, figure out the number of ways you could pick the first digit, second digit, and third digit, keeping in mind that repetition is not allowed. And then unpause to check your work. So in the first digit, we kind of have a clean slate. We know there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are options. In all, that's 10 options available. So I could pick from any of these 10 options. However, once I've picked my first digit, whatever one of those 10 digits it becomes, that digit cannot be reused in the second or third digits. So I've used up one of the 10 options, which means there's only 9 available for the second digit. Now, in terms of thinking of the third digit, I can't use either of the two that I've used for the first or the second. So 2 of the 10 digits are off the table. That leaves only 8 digits remaining here. And for this particular problem, we would just leave this as our final answer. 26 times 25 times 24 times 10 times 9 times 8. It's a large enough number that it would either come out in your calculator in scientific notation or a number with many, many digits. So for very large results, just leave it in the multiplicative form. As you go about your homework problems in this section, always ask yourself, is repetition allowed or is it not? Because as you can see in these two examples that we just completed, the thought process will change if repetition is allowed or if it's not allowed. We have a 4-digit number is constructed using only the digits 1, 2, 3. So notice here they specifically told us you can only use these digits. So for this particular problem, 4 is not an option. Neither is 5, 6, 7, 8, 9, or 0. We can only use 1, 2, or 3. They ask us how many numbers are possible, key phrase, assuming repetition is allowed. Now the whole part of these problems in this section is being able to take an overall process and break it down into the correct number of individual steps. Then once you've broken it down to individual steps, figure out the number of ways each of those steps could occur, multiply all of that together, and that's the number of ways the process occurs. So the first key step that you must make as a student solving these problems is identifying for the described situation how many steps could I break it into. So I would encourage you to take a moment and pause the video now and reread the information given here and ask yourself, how many steps could I break this process into? How would I describe those verbally? And then, how many ways could each of those individual steps occur? After you've taken time to think about it and attempt it on your own, unpause the video to check your work. So our key phrase here is a 4-digit number. That means there's 4 different digits written together. So I've got something in the ones place, the tens place, the hundreds place, and the thousands place. So I like to write down these brackets to help me focus on each step. Again, they're just organizational, but I'm going to continue with that process. So I'm going to say this is my first digit. And I know since it's the fourth from the right, it would actually be the thousandths place. Next up is the second digit. Then I need to pick the third digit. And then I need to pick the fourth digit since it's a fourth digit number. Now, keeping in mind how this was phrased with what I've underlined in red, would this be an appropriate choice of a 4-digit number? Is this a possible example? No. The problem here lies in the fourth digit, 4. I was told I could only use the digits 1, 2, or 3. So of the digits available, there are 3 original digits available to use, 1, 2, or 3. I also know that repetition is allowed, so I could have the number 1, 1, 1, 1. Or I could have the number 1, 2, 2, 2. The key idea is I can repeat digits, but I can only work from the digits 1, 2, and 3. So how many ways could I pick the first digit? Well, I could use either 1, 2, or 3. That means there's 3 ways in all. So I put down 3 ways to pick the first digit. How many ways could I pick the second digit? Well, since repetition is allowed, I still have all the original 3 digits available to be used. So there's still 3 options for the second digit. Since repetition is allowed, there's 3 options for the third, 3 options for the fourth. Multiply that together. Now this is a small enough number that we could write it as either 3 multiplied by itself 4 times is 3 to the fourth. Type this into your calculator and you'll get this is equal to 81. So there are 81 ways to construct a 4-digit number that uses the digits 1, 2, and 3 where repetition is allowed. Now, as a related problem, we're asked how many of these numbers are odd and less than 2,000. So let's think, what are some ways that we could go about solving this problem? I guess one way is I could write out all 81 4-digit numbers that are using the digits 1, 2, and 3 with repetition. And then from that list of 81 numbers, I could just X out anything that's even. I could X out anything that's greater than 2,000. And only the remaining digits should be counted. And that would be how many numbers from this group are odd and less than 2,000. However, that would be a very time-consuming process to first write out all 81 of these options and then X out anything that is not odd or not less than 2,000. Assuming we didn't make any mistakes, we would then have to count up the remaining options. So that is a possibility, but based on the amount of time it takes, it's not going to be a profitable one for us to go through. So instead, we want to really understand this descriptor of odd and less than 2,000. How can we make sense of this in terms of our 4-step process? Because we understand this breaking it up into separate steps. So we need to be able to phrase what does odd or less than 2,000 mean in terms of these 4 steps. Well, whenever you're trying to see if a number is less than 2,000, and for instance, I had these numbers written. What digit do you look at to see if a number is less than 2,000? Look at these 2, and what digit tells you whether it's less than 2,000 or greater than 2,000? Would y'all agree that that's what we are calling our first digit? If the number in the first digit's place is 2 or greater, the number is greater than 2,000. However, if the number in the first digit is less than 2, specifically in this example, the only number less than 2 that we're allowed is 1, the number's less than 2,000. So in order to get a number for our first digit less than 2000, the only one of the 3 digits we were allowed at the beginning that could be used is 1. So we have only one option here. Instead of the original 3, I could not choose 1, 2, or 3 anymore because choosing a 2 would make a number greater than 2000. Choosing a 3 would make something in the 3000s also greater than 2000s. I could only choose a digit 1 here in order to ensure that my overall number is less than 2000. At this point, I would encourage you to gauge how well you understand that thought process. And if it's a little shaky, go back in the video to where we first introduced this portion of the problem and then replay it. And take a moment to even pause the video and think about it. Definitely email me if you have questions. And once you feel confident about the idea that to be less than 2000 is a property of the first digit, then continue on with the rest of this problem solving. So we've been able to phrase in a counting-based argument what it means to be less than 2000. Next, let's focus on, based on our 4 digits that we count, which one of the 4 digits has the property that makes the problem odd. To help us see this, I'm going to write down a few different options of 4-digit numbers that fit our criteria of using digits 1, 2, and 3 that are specifically less than 2000. And I want you to focus on what property in those numbers makes the number odd. Look at these 8 4-digit numbers that I've listed, and then think about which one of these or which of these 8 numbers would be considered an odd number. What's considered the odd numbers? These 4. What is the property of these 4 that I've highlighted that makes them odd? The way you determine an odd number or an even number is always the last digit. A 4-digit number is odd if its last digit is odd. Similarly, a 4-digit number is even if its last digit is even. So when they say that we want an odd number, this means I must ensure the last digit is odd. Now we had 3 options to begin with that we could choose from, 1, 2, or 3. How many of these 3 options are odd? 1 and 3. So basically, if I want my 4-digit number to be odd, I cannot have a 2 as the last digit because that will make the 4-digit number even no matter what the earlier digits were. So when I'm thinking about this process, I've got my 2nd digit, I've got my 3rd digit, but in order to make sure the number's odd, I have to focus on the 4th digit. So as we said before, anything that involves special restrictions, deal with that first. We've already dealt with the 1st digit because it's what makes our number less than 2000. Now we're going to deal with the 4th digit because it's what makes our number odd. And I know in order for the thing to be odd, the last digit must be odd. Of the options available to us, how many of those are odd? Well, I could pick 1 or I could pick 3. That is 2 options. So there's 2 options here. And again, as you do these problems, keep in mind, I'm not saying that we choose the number 2, right? I'm saying there's 2 options. What are the 2 options? Either 1 or 3. Now with this in mind, we have now ensured that our number is odd. We've ensured that it's less than 2000. So there's no more restrictions that could be met, and that means we could choose anything that was originally acceptable to go in our 2nd or 3rd digit. So we were still okay with repetition. And in terms of the 2nd or 3rd digit, I could choose from either 1, 2, or 3. So there's 3 options for the 2nd digit, 3 options for the 3rd digit. The reason that we had special restrictions in our 1st and our 4th place is because those placeholders are what have to do with being less than 2000 and being odd. Any of the other digits just fit the original restrictions of using the digits 1, 2, or 3 and allowing repetition. And that's why we still had 3 options available here. So multiply all these together and that gives you the overall amount, 1 times 3 times 3 times 2 is 18. So there's 18 of the original 81 four-digit numbers using 1, 2, or 3 in repetition, which happen to be odd and less than 2,000. So whenever we're asked how many of the numbers that we were thinking about fit particular criteria, you need to be able to rephrase that criteria in terms of a restriction on one of the steps of the original process. And as just an introduction to the idea, if they ask you to make the number even, in order to be an even number, the last digit must be an even number. So if a problem asks you to make the number even, they're really giving you a restriction on the last digit, that it must be even. Similarly, if you're asked to make a number odd, then its last digit must be odd. Similarly, if they asked for a number to be less than 7,000, and I just picked 7,000 as an example, this principle applies in general if you think about it similarly for different restrictions. That's really a criteria on the first digit. In order for a number to be less than 7,000, its first digit must be less than 7. So the allowable options are 1, 2, 3, 4, 5, or 6 for the first digit. Now, I'd like to point out here why I'm not including 0. Why is 0 not in this list? Because 0 is less than 7. The reason 0 is not in this list is consider the number 0, 1, 2, 3. Now, technically there are 4 digits written, but isn't this really the same thing as 123? It's just written in a very weird way, 0, 1, 2, 3. The reason we don't allow 0 in the options here to construct our 4-digit number less than 7,000 is because if you have a 0 in the first place, it's actually not a 4-digit number or whatever digit you're trying to create. If there's a 0 in the first place, it actually makes the number that you're representing 1 less than you intended. So 0 is not in this list, not because we wanted to have a number less than 7,000, but because we wanted to ensure the exact amount of digits mentioned in the problem. So keep these 3 criteria in mind, and they will be helpful as you go through different problems to realize the phrase of the number must be even is a restriction on the last digit. The phrase the number must be odd is a restriction on the last digit. Saying a number must be less than or greater than some value means that's a restriction on the first digit. And you just have to think through how many ways can I still meet that restriction with the original restrictions of the problem. So I definitely encourage you to take some time, work through the homework problems. The only way we can feel comfortable with these new ideas is if we practice them, and as we have questions, reach out to me, the instructor, and I'll be happy to help you.